In this demonstration, I would like to show how to use the Numpy polynomial fit function. And this is the algorithm implementation of least squares polynomial fit. So the essential arguments in this function are the x vector, y vector, and the degree of the polynomial to be fitted. So I have developed an example. So the exponential curve, which is y equal y naught e raised to the power minus lambda t. This is the famous radioactive decay law, where the activity y varies with the time. So I have the libraries imported, the vector creation library Numpy, and the plot creating library matplotlib.pyplot. So they are in my program. And now in this cell, I have defined the lambda value as 0.03. It must be in the inverse units of the half-life of the radionuclide. Here is a creation of time array. Uh, well, let me introduce here the decay constant, and it is in inverse time units. Okay, this is the time vector. So for example, it starts from 0 to 100. These are the endpoints. And how many points are to be taken in this vector? They are 20. I have defined the initial activity y naught is initial activity. And here is the expression for the calculation of y vector, which means the activity values with different times. So it is just the calculation of this function y naught e raised to the power minus lambda t. Okay, after the calculation of vectors, this is the plot command plt from this library, plot ty with red circles, and the similar command to represent a line joining the points, and the x label for time and y label is the activity. So it creates a plot which seems to be correctly the exponential. But if our starting point is the data, if our starting point is the x and y data, can we see whether it is exponential or not? So in this case, we would like to take the log of this equation. So for example, if I take the natural log of this equation, so it will become, you write it here. Okay. So for the exponential curve, it was y equal y naught e raised to the power minus lambda t. So if I take the log, so it will become log of y naught minus e raised to the power lambda t. So which becomes a simple structure of a straight line if I define log of y as a capital Y and capital X as t. So I can write the equation of a straight line as y equals mx plus c, where with these equivalences, the m or the slope value will turn out to be minus lambda, and the constant c will be equal to log of y naught, log of y naught. So with these transformations, I can proceed to implement the least square fitting. So here we go. I add a code calculation part. Okay, here. So I can define capital X equal to time t vector, and capital Y is equal to natural log. So I have to pick up from the NumPy library log of y, and then I can call the function. So fit linear fitting, it is equal to NumPy polynomial dot polynomial. That's the root to get to that one, and then polyfit. So now it will be on x, y, and I have to set the degree equal to 1. So the code has not returned any error. Therefore, it means the fit has been generated. Fit vector has been generated. Okay. So it contains two values. So the slope value, the lambda value is minus 0.03, and the other value is 4.6, which was the intercept. So lambda value, which is exactly the same. So this is the slope value, and this is the intercept. So from the intercept, we have to get the value of initial activity. So if I get the y initial, so it is equal to exp of from the first element, from first element of the fit vector. So y initial, and I expect a value 100. So accurate. So it means that strategy works, right? There is another scheme to see whether there is exponential relationship between x and y. That instead of computing the log of the vertical axis variable, instead of computing the log, we can change the scale. There is the logarithmic scale as well, and in Python we can generate that one, and the data would appear as a straight line. So I generate another plot between time and the activity. So NumPy, so not that one. It is plt dot plot time and y, and okay, red circles, plt plot ty and blue line. Okay, plt x label is t and plt y label y. So this is going to create again the same graph, right? But now I'm going to make another line, another option from the PLT. So I say y scale to log. So it will convert the vertical scale to log. So behold, this is a crucial point in this demonstration. So behold, and seeing is believing. Seeing is believing. The data turned onto a straight line, right? So this is a direct indication. If you plot the exponential data on a semi-log scale, where vertical scale is logarithmic, the horizontal scale is a linear scale, then it is a direct and quick indication without implementing the least square fitting. So it is apparently it will show you that the scale is logarithmic. And now see the a bit of details from it. I turn on another option to allow seeing the grid lines. So you will see the scale has different kind of spacing. which is apparent from the ticks, that this is 10 raised to power 1 label, and the other unit is 10 raised to power 2. Right? So if I turn the grid on, so you will be able to see the lines. Okay. Yes, here it is. But only the grid lines on x-axis have been shown. If I need the finer grid lines, say minor, um, should it be true? Oh, this is not a valid expression. We try this one. Still not accepted. And with my memory, I think I cannot make it better. So I pause the recording for some time. I was trying to attempt an option for retrieving the grid lines to be plotted truly on the scale. So I figured that out. So here it is now. So I have to set both. So grid lines have been generated. And now I would like to extend the vertical scale to represent its pattern. So I choose y limits, the definition of y limits. So I use 1 to 1 e raised to the power 2. So 1 to 100. So that we can see the cycles of the logarithmic scale. So the scale is interesting. It retains the information that the straight line is there, which means the exponential relationship is there between y and t. And the other interesting option, that if it starts from 1, so 1 to 10, there is the major unit, and the next major unit is multiple of the first unit. So it extends to 100, right? So to read that one, this is the value 1, then this is the value 2, the value 3, 4, 5, and so on. And similarly, when we move in this segment of the graph, so the first value is 100, 10, the next value is going to be 20, then 30, and so on. And likewise, it extends in both the directions. So there is not going to be anywhere zero value for the vertical axis, right? And as a crude approximation to get the lambda value, so pick any of the 2 points. So since I have defined the vector t with 20 values, so I can define on the basis of the true expression. Let me explain that point as well. While taking the logarithmic scale, we do not change the values. So in order to extract the equation, we have to get back to the main equation. So like we will say, at t1, the value is y1, and at t2, the value is y2. So we have to construct two equations. Y2 equals y naught e raised to the power minus lambda t1, and y1 is y naught e raised to the power minus lambda t2. We divide these two equations to get the value of lambda and y naught. So first attempt, divide the two equations. So we will get minus y2 and with y t2, and this should be with t1. So therefore it will be minus t2 minus t1, and there is going to be lambda. And then you can define the lambda value as log of y2 over y1 and divided by t2 minus t1, and there is going to be the negative sign. So you can take any value for the pair t1 y1 and any value of any pair for t2 and y2. So let's implement that. So expected value of lambda. So I say it is lambda expected. So this can be calculated as negative of numpy by log of. So I can take any value. So for example, the fifth value divided by y of third value, and likewise whole divided by t fifth value minus 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 t third value, right? It is analogous to calculating the slope for the straight line y2 minus y1. However, we have to use here the logarithmic thing. Okay, so lambda expected value e. So we expect a value 0.03, and that's it. We got it. 0.02999999, which is the value we started with. So this is the equivalence of two methodologies. A quick way to get the exponential recognition is to plot the data on semi-logarithmic scale. However, on semi-logarithmic scale, we do not barely calculate the slope like y2 minus y1, right? We have to make a modified calculation, and that is with the mathematical expression, a calculation which is consistent with the mathematical expression of the function, right? So we cannot blindly apply for every straight line y2 minus y1 over x2 minus x1 as an expression for slope. This is a straight line, however, on a scale which is already scaled, in which the vertical axis is logarithmically scaled. So with this success, let's stop at this point. Take a deep breath. It calms the mind.